Okay, let's go ahead and get started. So today we're continuing with set theory. In the last lecture that I posted to YouTube, I introduced the definition of a set, as well as various operations on a given set. Today we're going to look again at set operations. Okay. Involving two or more sets. Okay, so the first, so I'm going to go ahead and just say let A and B be sets. And the first operation we're going to look at is called the union. So the union of A and B is the set A union B is equal to all X such that X is in A or X is in B. Okay, so this is the union of two sets. Okay, and again, this is using set builder notation. So what goes inside this set? All X such that X is an element of A or X is an element of B. And we can represent this with a picture called a Venn diagram. So suppose this is the universal set U, which consists of all elements that are possible when you're considering a collection of elements. And then suppose we have maybe set A and set B. So anything inside there belongs to A, anything inside there belongs to B. And this set is going to consist of everything that satisfies this with this being a tautology, right? So the OR operator, or the disjunction, is true whenever at least one of these is true. So if X is in A, this is true, it'll be in here. If X is in B, this is true, and this whole thing is true, it'll be in there. So with the picture, we can say everything that's in A is in there, together with everything in B. Okay? So that would be the collection of all elements that are in A or B. Okay? All right, so the definition. The intersection of A and B is the set A intersect B, which is equal to the set of all X such that X is in A and X is in B. Okay? So in order for something to belong in this set, the intersection, this conjunction with the AND operator needs to be true. And if you recall from logic, this is only true when that's true and that's true, right? So if we look at another Venn diagram here, here's A, here's B, okay? And if I pick something like right there, that satisfies being true in A, but it's not contained in B. So this would be true and false. which is false. So that would not belong to the intersection. The same thing if I picked something right here, right? It would be true for B, but not in A, so this would be false. The only elements that will make this true are the elements that are common to both of the sets. So everything here. Because anything inside there belongs to both A and B. However, there is another case where, suppose this is your universal set U, and here's A, and here's B. The two sets do not have to share anything in common, right? So in this case, the intersection is going to be the empty set, the set containing no elements. So just note that if A intersect B is the empty set, then A and B are said to be disjoint. Okay, so if their intersection is empty, they're disjoint sets. This is again the definition of the intersection. Okay. All right, so we have a few more definitions. A set difference B is the set A set difference B, so it's like A minus B. This is the set of all X such that X is in A and X is not in B. Now, notice here that the order for which you do this subtraction matters, right? Because B, so put this in parentheses, so B set difference A is a set of all X such that X is in B and X is not in A. So these are that's a different set than that. Okay? So using a Venn diagram, we have a set A, we have B. The only elements that will belong to A set difference B are the elements that make this true right here. So X is in A and X is not in B. Okay? And the only elements that will satisfy that with this picture here are these. All the elements that are in A but not in B. Okay? So this is set difference. Okay?
I have a question.
Yeah.
Yeah, what is that symbol after the and between the X and the B? At the bottom?
Here?
No, lower. Like, you know how it's and X?
Oh, X
Is that not or?
not in B.
Oh, got it. All right, thank you.
It's the element symbol with the line going through it.
Oh, got it. All right, thank you.
And
Real quick, also you had mentioned that the third Venn diagram is the empty set.
well, here.
What did you say about the empty set?
So here, the intersection here contains no elements because there's no elements to A and B.
Right.
So the intersection here is empty.
Oh, okay.
So the intersection here is empty.
Okay.
And, when that's the case, they're said to be disjoint. There's no overlap between the two sets.
Okay, I see. Thank you.
Okay. So now there's one more important operation. So one more of these definitions. So the complement of A is the set A bar, which is equal to the set of X such that X is not in A. Some people also use the notation, in some textbooks also use the notation A with the superscript C. Either one of these is valid, just it depends on what your textbook is using at the time. Okay. In this, if you look at a Venn diagram, if this is the set A there, then everything outside of A is in a complement. Okay, so all of this out here. Okay. All right, so those are the basic set operations. Now, you should notice that these operations act like the logical operators that we were studying in the logic section. For example, the complement, right? The complement behaves like the negation, and like you negate X being an A and you have the complement of A. The union acts like the OR between two sets. The intersection is like the AND, right? So there are similarities here. So if you're doing well with the logic portion of the course, then you should do well with the set portion of the course. Okay. So now let's establish set identities. If you recall from the logic sections, there were logical identities. In a similar fashion, there's going to be set identities.
All right, real quick, you had said that which one is like the OR?
The union.
Union, okay, thank you.
It's like the OR, and the intersection is like the AND. Okay, so I have a claim in the proof. So if A and B are sets, then the complement of A union B is equal to the intersection of the complements. Okay? So we can establish this using just the definitions that I just wrote down, along with the knowledge we have of logical identities. Does anyone see what this kind of looks like? It looks like something from logic that we use quite a bit. Any guesses?
Proof by contrapositive?
Not by like a proof technique, but by a law from logic. What does it look like to you? Think about what I said a second ago. The OR is like the union, and the AND is like the intersection.
De Morgan's?
Right. So this is actually one of De Morgan's laws for sets. And we can prove it by using De Morgan's law for logic. So let's go ahead and prove this. So we can just start on one side of this equation and then establish a string of set identities. So let's start on the left-hand side. So we have A union B complement. Well, that's by definition the set of all x such that x is not in A union B, right? That's just the definition of it. The complement of a set is just saying that x is not in whatever you're looking at. Right? In this case, it happens to be the union of two sets. Well, using what we know from logic, we can say that this is like negating the statement or the proposition that x is an element of A union B. Right? This is equivalent to that. You're negating x being in there. It's like saying x is not in there. Okay? But now, what we can do, if x is in the union, right, then x has to be in both sets. Right? Or another way of saying that is that x is an element of A, or x is an element of B. That's another way of writing that, right? This is the definition of being in the union. Right? X is in A or x is in B. But now we see that we're negating an or, right? So this is equivalent to the set of all x such that it is not the case that x is in A, and it is not the case that x is in B. And this was by De Morgan's law. From logic, right? You negate an or, and it becomes the negation of the and, right? The and of the negation, I'm sorry. But now we can rewrite this and say that it is not the case that x is in A. Another way of writing that is saying that x is not in A. And we negate this here and get that x is not in B. Okay? But here, right, if x is not in A and x is not in B, right? Well, if x is not in A, then x is in A complement, because you're either in A or A complement. So this is the set of all x such that x is in A complement, and x is in B complement. But now if x is in this set and x is in this set, then it's in the intersection of those sets. And then we're done. Because this is just the set A complement and B complement. Done. Because the right-hand side equals the left-hand side, we've established this claim. Okay? So on your own, you should prove the other De Morgan's law from sets. So we try proving the complement of the intersection is equal to the union of the complements. if you basically mimic exactly what I did here, then you should be able to establish that set identity. Okay. So let's see. Another identity we can establish. I haven't shown you yet how to prove subsets. Okay, so let's look at one of these. Okay, so let's see. A minus B minus C is a subset of A minus C. Okay, so let A, B, and C. So if A, B, and C are sets, then A minus, let's see, A set difference B, set difference C is a subset of, say, A minus C. Actually, we'll come back to this one. Let me do it, and no, this is fine. It shouldn't be too hard. So how do we do this? This is like a remark. To show a set is a subset of another set. Show that any element of the first set must belong to the second set. Okay, so this is how you can show a set to be a subset of another. All right, so let's look at the proof here. See if we can figure it out just by using definitions. So again, you probably want scratch work on the side, but I'm just going to walk through it. So I'm going to say let X be an element of A set difference B set difference C. Okay, so what have I done here? I want to show that this set here is a subset of that, which means that I want to show that any element in here must belong there, right? So in my first sentence here, I'm picking an arbitrary element here. X is just some arbitrary element in that set, okay? So once I've picked that, now I can use the definition to see what's going on with X. Where does X belong? So then, by definition, if X is in this set, it means that X is in the first one and X is not in the second one. And then X is in A set difference B, and X is not in C. Now here, what you really want to say is and, like use the word and instead of using the logical operator, because now we're starting to write out a more formal proof. But you see that this is true, right? If X is in this set difference, then it belongs to this one and not that one. It belongs to the first one and not the second one. Okay? So now in particular, we now see that X is in A minus B, right? You see that right here? So therefore, X is in A and X is not in B. So therefore, X is in A and X is not in B by definition of X in A minus B. Just so the reader will know why you said that and that. Again, that's just a definition of the set difference. It's in the first one and not in the second one. So notice here that X is in A and X is not in C. So we can say something like, in particular, X is in A and X is not in C. It follows that X is in A minus C. And then you're done. Why? Because you've picked an arbitrary X in that set and then shown that that same X must also belong to that set, which establishes that this is a subset of that, because anything in there must also belong in there. Okay? So this is a subset proof by, sometimes people call it an element argument, where you pick an element in one set and show that it must also belong to the other set. Okay? So, these are typically not too bad. This one was kind of this is, as far as showing subsets right now, this is probably like one of the harder ones you'll see. The other ones are pretty simple. Okay, so let's look at another equality, I suppose. Okay, so if A and B are sets, then A A set difference B is equal to A intersect B complement. Okay. Okay, so there's two ways to do this actually, to establish equalities. One is by, so I'll go ahead and do both of them. So this is proof version 1. It's very simple, you just start on one side, write down the definition. So x is in A, and x is not in B. But then if x is not in B, then it must be in B complement. Okay. Now here, we see that the intersection of x being in one set and x being in another set, that's the same thing as being in the same thing as being in the intersection. So x is in A, intersect B complement, and then we're done. Okay, so actually this one's too simple to prove the other way, really. Another way of establishing equality is to show that this is a subset of that, and that is also a subset of that. It's another way to establish this equality. Okay. So, I think that should do it on the proofs here. But there's one more operation that we should talk about before we end it for today. And that is, so let A1, A2, dot, 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 AN be sets. So then this is notation for you. So this is a big union sign. I equals 1 to N of A sub I. This is the same thing as saying A1 union A2 union dot 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 union all the way to A N. And then for the intersection, there's the big intersection symbol. I is equal 1 to N. This is equal to A sub 1, intersect A sub 2, intersect dot dot dot, intersect A sub N. So this is just notation to look at, oh. So all this is doing is subscripting a bunch of intersections and unions. In particular, you start at the lower index and you end at the top index, and this is the operator that you're using. It's similar to big summation notation that some of you might have seen in the past. Okay? So, maybe we can look at some examples of these summations here. So, let A sub I be the set consisting of negative I and I. Okay, so a sub 1 is equal to negative 1 comma 1. A sub 2 is equal to negative 2 comma 1, positive 2, so forth and so on. So if we want to look at maybe the union from I is equal 1 to n of a sub I, then we're taking the union over all of these pieces here. So this will be negative 1 comma 1 union negative 2 comma 2 union, I'll just do one more, negative 3 comma 3 union dot 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 to the union of negative n comma n. Okay, so altogether this should look like this. So it'd be negative 1, 1, negative 2, 2, negative 3, 3, dot dot dot, all the way up to n, where n is a positive integer. The intersection here, however, of all of these sets, well, I'll write it out just to be clear. So it's that set intersect a sub 2 intersect dot 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 all the way to the intersect of negative n and n. Okay. So here, does that set here, the first a sub 1, share any common elements with a sub 2? Are there anything that is shared between those?
No.
No, right? This only has negative 1 and 1. This only has negative 2. So that's going to be empty. And then none of these other sets will share anything with them, right? So this is actually going to be the empty set. Because these are all disjoint from each other. They don't share any common elements. Okay? So I guess that will end it for today's lecture. I know that I've received a few emails over the weekend from students about the first exam and how to turn it in. So Monday, Wednesday classes, I want you to email me your exam on Wednesday. Tuesday, Thursday, email it to me on Thursday. If you already emailed it to me, just email me again so I'll have it. And then also, let me share my screen. If you look at the exam, these are the instructions here. So you do have 4 continuous hours to complete the exam. I saw some questions about that. And, okay, then back here. Maybe it was an announcement that I made. I'll put down formal instructions on how to submit the exam. I'll do that later today, and just follow those instructions on either Wednesday for Monday, Wednesday classes, or Thursday for Tuesday, Thursday classes. Okay. So that should be it. Also, be sure to keep up with the Zybooks homework. you should be at least on the set theory portion of the Zybox homework by now, all right? Okay, so that will be it for today. Just email me if you have any questions. I should get to all the previous emails by the end of the day. There's a few that I need to go through, so I'll talk to you soon. Nope, it seems I have a, let's see. I got a question on when we will code again. We probably won't code again until next week, so next Monday. Okay. So that will be it for today. And stay safe, and I'll see you soon.